Good morning. Thanks very much for attending PyData. We got the first session in this room. The first speaker, we have a data science lead from Meta, traveling from just from Paris yesterday. So we're going to talk about lifetime value and forecasting through PySTAN. So if you would like to all give Raphael Tamaki a big clap.
Thank you, Ed. Thank you, everyone, that decided today to have this presentation as your first one for this whole conference. I hope you will like it, but I will say that I'm going to take probably most of the budget for a number of slides, so I'm going to be quite fast here. I think I just have made over 100. So prepare yourself. I hope you took a good amount of coffee. So let's start off. So just a little bit short about myself. So I'm a data science lead in the market science department at Meta, where I apply causal inference techniques to help advertisers increase the effectiveness of their marketing investments. I'm also a maintainer of GeoLift, which is an open source technique for measuring market effectiveness using geographic quasi experiments. Prior to that, I worked as a staff data science at Wildlife Studio, which is a mobile game developer and publisher. There, I was a tech lead for the lifetime value team, where I developed lifetime value models for launch of 5 different games. And I additionally also implemented ads monetization algorithms that help increase the revenue of the games in the company. This presentation is going to be divided in 2 parts. First, I'll give you a short introduction about advertising for digital products and the reason and motivation behind why we should use a probabilistic modeling when we are estimating LTV. Hopefully that will be clear after some 8 minutes, and then I will show you how you can use PySTAN to forecast LTV. I will describe a little bit about the data set that I'm going to use for this example, describe the mathematical model, and show how you can implement that both in PySTAN, which is the title of this presentation, but also in PyMC. I will finish up by comparing these 2 libraries in terms of computation performance, so that you have at least some idea of in which situation you should use either one of them. So let's start off with modeling advertisement for digital products. Let's suppose that you have a mobile game. And this mobile game, you have the possibility to find it, let's say, in Apple or Google Play Store, install it, and enjoy it after a little bit. So what would happen is that people would find your game naturally, install it, and this cycle repeats every day. Some days are going to get more users, some days are going to get less users, but every day you're going to get some users that find your app naturally, that find your app organically just by looking at the App Store. However, that is just a small portion of all the people that could actually find your game, that could actually download it and enjoy it. And that's one of the main reasons why companies use these digital platforms, such as Twitter, Google, TikTok, Facebook, among others. Though probably I should not be using Twitter right now, right? Let's take an example and select, let's say, Twitter. After you select one of these digital platforms, you can be even more specific about the type of people that you want to reach out. You can define extra characteristics about the people that are going to see the ads of your game. Let's say you can define women, you may define that they have 50 years plus, maybe only those that use iPhone or live in the Netherlands. Whatever you decide to choose, this combination of digital platform and additional characteristics is going to define the target population, the audience that can see your ad. It's not going to be that all of them are going to, but it's going to be all that could. After you do that, what's going to happen is that you're going to start investing money in this digital platform to show ads to these people, and so that some of these people will find it interesting, download it, enjoy it, and hopefully for your company that they spend some money on it. And the cycle is going to be repeated every day. So some days you're going to invest more money, and as a consequence, you're going to get more users. And some days you're going to invest less money and get some less users. And if you were to have a closer look at what is actually happening there, we'd see that depending on the target population that is selected, for example, this green line here, it could happen that you have a lot of users installing your game just by using a small bit, but that quickly saturates at a lower point. But if you decide to use a different target audience, or let's say even optimization, you would have very low downloads at the very beginning with a low bid, but that number of downloads will increase as you increase the bid much more rapidly, and you have a much higher number of downloads as a consequence. So depending on the target audience and your bid, you may have very different number of downloads that are from your marketing campaign. So this cycle can be described in this diagram here, which has 3 steps. The first step is where you define what is the number of downloads that you're going to get. And as I just described, it depends on the target audience that you selected and the bid that you're using to operate your marketing campaign. So, and process is what I'm going to call here for the rest of this presentation as the volume function. How does the bid affect the number of downloads? Next, you have to transform downloads into revenue. And to that is what I'm going to call here the lifetime value. So how much revenue does each one of these users generate on average? And lastly, we have the profit, which is just the difference between revenue and cost. And when you're operating a marketing campaign, what you want to do is find the bid that generates the highest profit. So how can you find it? Well, let's take a closer look again at the profit equation here. If we were to expand this to the revenue and cost, what we would see is that revenue is just the multiplication of downloads and LTV. And similarly, cost is the multiplication of downloads and the bid, how much you pay to get each one of these users on average. This can be further simplified. And then I can substitute downloads by the volume function that I described before, so that we have an equation that depends on LTV, bid, and this volume function. The LTV, at least in this presentation, at least under some constraints, you can assume that it can be constant when you are making the bid itself, so that when you define the target audience and for the duration of your campaign, your LTV is not going to be depending on the bid or going to change dramatically from one point of the other. And similarly, the volume function, again, is defined by the target population that you said at the very beginning. So, for example, in this case, we could have select Twitter, women of 50 years plus of age, iPhone, Netherlands. And with that defined, it's probably not going to be changing dramatically over the duration of your campaign. So much that your profit equation can be simplified as a function of the bid. And if you were to experiment with very many different bids, higher, lower, what you would get as a consequence is a curve that looks like this orange one here. And this function has mainly 2 properties. One, if you bid 0, you are not going to get any downloads from this platform, and as a consequence, you're not going to get any revenue back. And also, if you bid exactly how much these users are worth, well, it doesn't matter how much downloads you get, you also get no profit out of it. And in between these 2 points, you're going to have profit. And in one specific point, you're going to have the highest profit possible. And the highest profit possible is actually a little bit easier to find if you know the LTV. And as I said, it's not going to change dramatically, at least on each bid. And also, the volume function is not going to change because you already defined the target audience for your marketing. So much that if you know how this volume function works as well as your LTV, you can find the optimal bidding point by just putting it in any optimizer that, well, basically exists in any programming language. And it's going to give you back the bid that generates the highest profit for your marketing campaign. However, I just said that you know your LTV, right? Well, actually don't know your LTV. That's one thing that we estimate. It's not something that you know from, let's say, out of the bat. And if it's an estimate, well, you are not going to be sure about it. You can be wrong, you can be overestimated, underestimated. So what is the role that this uncertainty play in your marketing strategy? Let's go back to the equation again and see what exactly happens when you don't know your LTV. When you don't know LTV, well, it basically means that your LTV can be under or overestimated. And if it's underestimated, what is going to happen is that you're going to think that your users are worth less than they actually are. And as a consequence, you're going to be bidding less than you actually should. And it's going to generate a lower profitability point for your marketing campaign. And similarly, if you overestimate your LTV, what's going to happen as a consequence is that you are also going to bid higher, in this case, much more than you should, and also not going to have as many revenue, as many profit as you actually should. This can be especially dangerous, depending on how much you overestimate. If you overestimate a lot, it's going to happen that your profit that you think your marketing is generating is very high, but the actual profit can be very low, even negative, so that you can take a long time, think that your marketing is generating like a lot of money, but actually you're just burning money out of it. So this can be a especially dangerous situation. And if you were to have a closer look at what's going to happen depending on the error level that have underestimating or overestimation, you're going to see this line here, where it's a little bit more clear that depending on how asymmetric this profit curve is, and again, this is usually a consequence of this volume function, how many downloads you get by how much you bid, you may have to underbid on your marketing campaigns. And as well, how much you underbid depends on how uncertain you are about your LTV. So much that when you are really uncertain about your LTV, how much you should be actually bidding, you have to be even more careful about how you bid. So depending on these two characters, the volume function and the uncertain, you have to bid differently on your marketing campaign. So, for example, you may have to be a fraction of actually the expected LTV that you are predicting. So how can you find your LTV? How can you find the distribution, the possible values that your marketing campaign can have? Well, you can use PySTAN. That's probably why you are all here, right? So what is PySTAN? Well, you probably already know, but PySTAN is actually just a Python interface to STAN. And STAN itself is a platform for statistical modeling that allows for high-performance statistical computation. It was released in 2012, and since then has seen wide use in the different scientific fields, partially because of the interface to both R and Python, but mainly because of its implementation of efficient sampling algorithms. So we are going again to touch what we just had on the talk before, on PyMC, on Markov chains, but I'm not actually going to describe anything that's going on there. So for this example, I'm going to use this lifetime value data set that is available from Kaggle, so you can probably use the same data that I'm going to. This data set was shared 3 years ago by David Rodrigues Sengado, and it contains anonymized data about users that subscribe to a product in a website. When they subscribe to this product, they have to pay a fee that is renewal, let's say, every month, every week, to have access to this product. This data set contains around 900,000 users' data. That is over 212 days. So if you were to have a look at how this data set is, you would see this head up here. So you would be able to see that we have many different characteristics about our users. We have when the user joined, the credit card level, which product they adopt, and even the country they come from. However, for simplification, I'm just going to focus on two of them, the join date and the target, the LTV. So much that if you were to plot these two so that the join date is on the x-axis and the target, the LTV, is the y-axis, what we'll see is this blue line here. Well, it'll look a little bit more black, right? In which we see in deep blue or black the average value, and in this light blue region, the 95% confidence interval. And what we are going to do here is use some training data to forecast the LTV in the future, let's say 5 days ahead. So what is the model that we are going to do for that? Well, let's go back to the process that I just described at the beginning of the presentation. In that, if we were to have a closer look at what is actually happening there, and remember what I said before, what we have is that every day we have this target population, and we get just a small sample out of it. We just get a small portion of all the people that we are targeting that we could actually have install our game. And this cycle repeats every day, so that every day we show some ads and get a small share, a small sample of these people. However, even though it's always the same people, we are always targeting the same population, it doesn't actually mean that the LTV can be the same from one day to the next, right? The LTV can change maybe because of different days of the week. Maybe it's weekend. Maybe they want to spend more. Maybe it's a different day of the month. Maybe they got just their paycheck. Maybe there is global economic change. Maybe there just occurred a pandemic overall in the world. So even though we have always the same people being targeted, the LTV may change from one day to the next. And one of the most simplest assumptions that we can make is that the LTV can be described as a random walk. So that we expect the LTV from one day to be the same LTV as the previous day, but following a normal distribution. And similarly, the LTV that we have on each one of our users is actually just a sampling process. So that in this case, I decide to use a normal distribution, could use other distributions as well, that have the expected value, the LTV of the population at the date that this user joined, but also with a normal distribution, here standard deviation sampling. So that our model can be described by these three equations. First is how we describe that the LTV follows a random walk. The LTV of our population follows a random walk. Next, we had the definition that the LTV of each one of our users, the LTV that we actually observe, follows also a normal distribution and is a sampling process. And the LTV, and then we have to define the prior for our parameters. In this case, I'm just going to show one, but which is the LTV of the population at the initial date. So how would we implement that model in PySTAN? Well, this is a very short simplification, but first you have to define and call stan, and then you have just two lines here. One is the build, where you're actually going to compile the model, and then the posterior distribution, where you're going to get the sample for your parameters. Let's just focus into the second line here. We have this time series model, which is a string, that is actually exactly the stan model that is going to happen in the back end, and the stan data, which is actually a dictionary. Stan, at least PySTAN, doesn't actually receive a data frame that you would normally be using, for example, as sklearn. It uses a dictionary. And in this dictionary, we are going to pass 4 arguments. First is the number of data points that we have for our data set, the number of users that we have. Then we have to define the number of dates in our training data. Then the dates that each one of our users joined, and observation with the LTV of each one of our users in the training data. With that clear, let's take a closer look of what is actually happening in the time series model. What is the actually model getting passed to stan? Stan models always have at least 3 blocks. It has the data block, which is where we define the kind of data that is going to be passed to the model. Then we have the parameters, where we declare the values that we want to estimate. And lastly, we have the model block, where we connect the parameters with the data. Let's have a closer look at what is happening in the data block. Again, remember that we just passed a dictionary. Again, the number of data points n is an integer. The number of dates also an integer, referring to the number of different dates that we have on our training data. Then we have the user level information. When each one of our users joined, which is a vector with n values, and an observation which is going to hold the LTV of each one of our users. And it's also going to be a vector with n different values. Then we can see what's going to actually happen with our model, how we can actually implement these equations in PySTAN. First, we have to define the LTV of our population, which is going to also be a vector with with a number of values equal to the number of dates in our training data. Then we have to define the standard deviations for our model, which both are going to be real numbers, real positive numbers at that. And then we can define, finally, the model itself. In basically any of the probabilistic modeling that you're going to do, both in PyMC or PySTAN, you are almost always going to start by declaring the priors for your parameters. In this case, I decided to call the prior for my parameters the standard deviation, a half Cauchy distribution. And for the first value of my LTV of the population, as a normal distribution, we expect the value 6 and standard deviation 3. Then we can define that the LTV of our population follows around the walk. And that is done by saying that the LTV of our users is expected to be the same value at the previous point, but following a normal distribution. And similarly, the LTV of each one of our users also follows a normal distribution, where we expect the LTV to be the LTV of the population when these users join, and the standard deviation, that is the sampling STDV here. As much that if you were to use the training data that I showed you at the beginning, that time series model, time series data, and this model that I just described, we're going to get this line here, where we see that the expected LTV of our data, the LTV population, is in blue. And you may think that it's not going to be fitting well, but actually we are not fitting the LTV that we observe on each one of the dates, the user level LTV, but actually what we expect the LTV of our population to be at that point. So as you'll see, that is not going to be following the noise that we have on the LTV of each given date. So much that after we have that, after we estimate our data, we can use the parameters to say, forecast the LTV in 5 days in the future. And we can do that, and if think that the LTV of our users, let's say, is 6, and even find the credible interval from 5% to 95%. And we can repeat this process for every day in our training data, so that every day we add an additional date to our training data and forecast 5 days in the future. If we repeat this process again and again, what we would see is this green line here, where you see that the expected value is in deep green, and the 95 credible interval. And this shows that where we expect the LTV of our population to be in any given point in the future. So I just show how we can implement that model in PySTAN, but what do we look in PyMC? Well, I'm going to go actually very fast here, but similar to that, we would call PyMC and just find the model. And we start by calling the prior for our parameters. Again, I'm using the same priors as before, standard normal distribution for my expected value of the LTV population, and a half Cauchy for both standard deviations. Then we have to define that the LTV of population follows around the walk, and the LTV of our users is also from a sampling process with a normal distribution. How would these two models compare in terms of performance, only performance? Well, it's not going to be a perfect benchmark. This is only going to compare this model and this data set. So if you try out again, you may see something different. But using this data set and using different number of users by doing a sampling process with replacement, so that I have 10,000, 20,000, 50,000, and 100,000. What I saw is that PyMC outperforms PySTAN after 20,000 data points. Before that, PySTAN is performing a little bit better than PyMC, so much that you can see here that, again, around 20,000, 10,000, 20,000, they are both very similar. But after 50, 100, PySTAN is clearly taking much longer than PyMC to generate the distributions of our parameters. However, this is only using the default samplers that you will be using if you are new to PyMC and PySTAN. If you were actually using some non-default samplers, actually they just released it a little bit better now. But there's still no default samplers, NumPy and NumPy. These do use a different backend than the default sampler. And if you do that, if you use NumPy and NumPy, you see a huge leap in terms of performance. You see that if you use NumPy and NumPy, you are going to take much, much less time than when you're using the default sampler. One point worth of attention, though, is that PyMC, because it's actually a much more maintained library, actually allow you for multiple implementations of the same model. For example, using different classes. And some classes can play significantly lower performance. So what I showed you before is the implementation above, where I'm only using statistical distributions to implement my random walk. If I use the Gaussian random walk that PyMC provides out of the bat, and at least that was my first implementation, it takes significantly longer. If you use the Gaussian random walk, you see almost it taking 3 times longer than when you were using the implementation that I showed just before. So what you can face if you're new to PyMC is that your model will maybe take longer because you are maybe using a class that is not optimized for what you're trying to do. Another thing that I would like to say is that what I tested just before is when I keep the number of my model the same, increase the number of data points. Another benchmark done by Joshua Cook, I think he's from the US, is when we keep the number of data points the same, the model is the same, but increase the number of groups, the number of different, let's say, combination of covariates and cardinality of your covariate itself, so that you may have, let's say, 10 different groups, 20 different groups, 100 different groups. This benchmark was actually doing STAN and PyMC3, which is the older version, but you can see that it's going to be a little bit consistent with what I just described. When your models are more complex, PyMC is going to take less time than STAN to do, to find your parameters. So what would be my summary here is that I would recommend people to use PyMC if your data set is large. If your models are complex, you have many covariates, high cardinality, hierarchical models. If there's a ready-to-use implementation available, for example, PyMC already provides you marketing mix models, lifetime value models, or if you can use the in-development samplers, NumPy and NumPy, that are much faster than the default one. And I recommend to use PySTAN if your data set isn't too large, your models aren't too complex, or you or your colleagues have experience working with STAN from another programming library like R. So in conclusion, depending on the properties of our marketing campaign, the uncertainty of our estimate may hugely impact the strategy and how you best operate them. We saw how we can implement the CLTV in PyMC or STAN. That PyMC performs better than STAN for larger data sets or more complex models, and that PyMC may have a slightly steeper learning curve, but can be worthwhile if you not have to implement something very fast, or if you want to do something very complex. I would like to thank especially Thomas Vickley from PyMC Labs. He was very important for me to do the best benchmark possible, ensuring that this benchmark is valid and appropriate with the current state of the library. And I'm open for questions. Thank you very much.